Hello and assalamualaikum to everyone. Okay, so basically, this is my second uh, second lectures on fundamentals of thermodynamics. Okay, so basically we proceed into the chapter for first law of thermodynamics. We have I have three parts, and in this session we have part one only lah. Okay, alright, so the first law of thermodynamics. So the first law basically is referred to law of conservation of energy, which is the energy cannot be destroyed or created, but rather it can be transformed to another state. Okay, so basically, in other words, the energy transferred into the system minus the energy transferred out of the system is equal to the change of energy in the system itself. So we can derive in mathematical model, something like this. So basically, energy in minus energy out is a change in the energy system. So normally we have three types of energy being transferred, which is heat, work, or we have a mass flow. Okay, and three types of change of energy in the system: change in internal energy, U, kinetic energy, and also the potential energy. So the figure is something like this. If we have a rock hanging from the cliff, so basically if the rock have not fallen yet, so we call it as a potential energy. Okay, if the rock has been fallen, so we call it as a kinetic energy developed by the rock. Okay, so based on the three types of energy transferred in or out of the system, the mathematical model of first law can be written as, so change in energy, change in heat, change in work, change in mass, minus change in heat, work, and also mass is equivalent to either internal energy, kinetic energy, or potential energy. Then we can rearrange the equation above, something like this. Yeah, we have the general equation. Then simplify the equation, we have change in heat, change in work, and change in mass flow. So we have the accumulation of internal energy, kinetic energy, and potential energy. So this is the we can see that change Q in Q out. Okay, so the icon here is the path function. So basically we call it as a process, we consider as a process. So here we call it as a state function. So basically either is the initial and final state of the process. Energy transfer by heat, we have capital letters of Q and also small letters of Q. So the difference between this is Q, smaller Q, have kilos. The capital Q, you don't have kilos. Okay, so you can differentiate between small q and the capital Q. Okay, so heat energy is the form of energy that is being transferred between the two systems. Basically, if you talk about energy, heat in particularly, there must be temperature difference. Heat, temperature. Okay, so for example, other than that, we have kinetic energy, we have difference in velocity. Potential energy, we have difference in height. Okay, So heat energy or thermal energy, or simply heat, is the form of energy transfers among a particle, atoms, in a substance or in a system by means of kinetic energy of those particles. In other words, under kinetic theory, the heat is transferred by particles bouncing into each other. Heat energy always refers to the transfer of energy between systems or bodies, or to energy contained within the system or bodies. So heat refers to total energy of the molecular motion or kinetic energy of a material, while temperature, on the other hand, is a measure of the average or apparent energy of molecular motion. In other words, heat is energy, while temperature is a measure of energy, which justify the entropy. Entropy, the second law of thermodynamics, okay, where your entropy is your heat, passing heat, divided by temperature. So in thermodynamics equation, heat is a quantity of energy, which may be transferred between two systems. For example, the path function depends on the process of transferring the heat. So in contrast, both temperature and internal energy are state functions. So as a form of energy, we use SI units. So SI unit, we have joule. Okay, so joule, okay, Newton meter per second. Though heat is frequently also measured in calorie, which is defined as the amount of heat required to raise the degree of temperature of 1 gram of water. Okay, so that is the amount of heat. So sign conventions of heat energy transfer. We got heat that is released to the surrounding, we referred in negative. Heat being absorbed, we referred as a positive. It's a normal convention lah. Okay, as long as you know which is being transferred, it's okay. A related term is heat flux, which is the rate of heat transfer per unit cross-section area. Okay, heat flux may be given in units of watts per square meter or joules per square meter, something like this. Okay, all right. So historical background on heat energy. So kinetic theory treats molecules as a tiny balls that are in motion and thus possess kinetic energy, whereby heat is the energy associated with the random motion of atoms and molecules. So heat transfer mechanism, you will more details on MEC 551 thermal engineering. We have three types: conduction, convection, and radiation. So this way you will found this in thermal engineering. Okay, for at current time we will not discuss this further lah. Okay, so energy being transferred. So energy transfer by work, we have W kilojoules. Okay, or works kilojoule per kg. So work, the energy transfer associated with force acting through distance, Newton times meter. Okay, the sign conventions for work done by a system are positive. Work done on a system we call it as a negative conventions. So in this course, we consider 4 modes of work transfer across the boundary of a system, as shown in the following diagram. So the first, we call it as a work shaft work. electrical work, spring work, and boundary work. This is your boundary inside here, substance, boundary. Heat versus work. Both are recognized as the boundaries of a system as they cross the boundaries. That is, both heat and work are boundary phenomena. System possess energy, but not heat or work. Both are associated with a process, not a state. Unlike properties, heat or work has no meanings at a state. Both are path function. So whereby, for example, their magnitudes depend on the path followed during a process as well as the end states. So this is the example of a path. Either it's a process A or process B. Alright. So basically something like this. These are properties of a point function. Okay. In exact differential, state 1 to state 2, you derive. So integrate, you have V2 volume 2 minus volume 1. So we have a change in volume. Alright, whereby path function have inexact differential. So we have path function, we have work 1 to 2. We don't have a change, we have a work 1 to 2. So this is the difference between the properties and also path function. So for example, we continue shaft work. So shaft is a force acting through a moment, arm, okay, that generates a torque. So your torque is equals to force times r, or your moment arm, or your radius. So this force acts through a rotational distance s at some number of revolution, n revolution of the shaft. So this is your revolution. Others may call it as a RPM, revolution per minute. So here the icon is S. So the formula will be 2 pi r times n, numbers of revolution. Thus, the work shaft is calculated as work, your force, times your numbers of revolution. So we got 2 pi n times T. T is your torque. So the power transmitted through the shaft is the shaft work done per unit time. So you got N dot. So N dot here is a quotation, a symbol of time, S. We have a units. So we got kilowatt. Electrical work. Electrical work is the work that is done on a system by electron, where n, number of columns of electron, move through a potential difference V. The electrical work done is work, voltage, times n, number of column. So in electrical power, work, voltage, time, ampere. When we have a potential difference and current change within time, we differentiate, integrate within the change of time. So we got your total work. Electrical work versus heat transfer process. So the main distinguish between electrical work and heat transfer process is the selection of the boundary. As example, let us consider a well-insulated electrical oven is being heated through its heating element. So, top figure. The system include the entire oven, including heater. So, the energy transfer to the oven is not caused by a temperature difference between the oven and the air. Instead, it is caused by electrical energy crossing the system boundary, and thus we call it as a work transfer. So, in bottom figure, the system only include the air in the oven without heater. With the heater has been left out. So the boundary is only on the air. So this time the system boundary includes the outer surface of the heater and will not cut through it. Therefore, no electron will be crossing the system boundary. Instead, the energy transfer is a result of temperature difference between the electrical heater and the air. So we call it as a work transfer process. So you must know the difference between work transfer and heat transfer process. So work transfer, we include the heater. Heat transfer, we exclude the heater. So the only crossing the border is only temperature difference. Spring work. When the length of a spring change by a difference amount, we call it as a dx. X is your distance. Under the influence of force F, the work done is work spring force time the x, the distance, change in distance. So for linear elastic spring, the displacement x is proportional. For linear elastic is proportional to the force applied. So whereby we have forces F is equal to kx, where k is the spring constant. So substitute and integrate yields. We have work of spring is equal to half k times x to the power of 2 minus x1 to the power of 2. We have units in kilojoules. So whereby we have x1 and x2 is the initial and final displacement, x1, x2. So we have the total work. So example problem 3.1. Okay, sample problem 3.1. A piston cylinder device contains 0.05 meter cube of a gas initially at 200 kPa. At this stage, a linear spring that has a spring constant of 150 kN per meter is touching the piston but exerting no force on it. Now, heat is transferred to the gas, causing the piston to rise and to compress the spring until the volume inside the cylinder doubles. If the cross-section area of the piston is 0.25 meter square, determine A. The final pressure inside the cylinder, B. The total work done by the gas, and C. The fraction of this work against the spring to compress it. Okay, so basically we have a spring work problem. Alright, so given directly is a volume 0.05 meter cube and your gas pressure is at 200 kPa, and the given X linear spring (150 kilonewton per meter. Okay, so A, the final pressure. Okay, given is the volume. So basically the volume, the final volume V2 is double V1. So which means we have the final volume is 2 times 0.05 meter cube. We got 0.1 meter cube. Okay, then we must search what is the displacement of the piston. Your x value for the movement of the volume. So your movement of the volume, change in volume, is equals to x A, area. Okay, so this is the, we have volume is meter cube, so we have meter dot meter square, so which means that we have also the same meter cube. Okay, so rearrange the equation. We have x is your difference in volume times your area. So we have 0.1 minus 0.05 meter cube times your area is your 0.25 meter square. So we have your area in meter. Sorry, the distance is in meter. Then the final, the force applied, Kx. So we have 150 kilonewton per meter times your this value m, so times your, we got kilonewton. Okay, and the pressure P is force divided by area. So your force, kilonewton, divided by area, meter square. So what is your area? Initial area. So this value you calculate before this. So we got kilonewton. Newton is force, Newton. Sorry. So Newton per meter square is a pressure. So you got kPa. Okay. So for B is the total work done by the gas. So from here you need to draw a schematic diagram. The illustration from the schematic diagram will facilitate your understanding more on how we determine the total work. Okay, so you have pressure, volume, this is a unit kPa. Alright, so from initial, okay, so if you have done calculate this, so the initial is 200. Okay, so initial volume is 0.05, and the final volt, let's say this is your value. So from the calculation we got 320. Okay, so the final volume you got 0.1. Okay, so from this area you can get the total work. Okay, as kPa times meter cube. Okay, you got Newton meter square times meter cube Newton meter. So you got Newton meter. So Newton meter is a work. Okay, so total area, this area, so you have work zero point 0.1 minus 0.05 times 200 plus over 2 0.1 minus 0.05 times 320 minus 200. So you got your final answer, Newton meter. Okay, alright, so number 3. C. The fraction of this work done against the spring to compress it. So work spring. Okay, is only by the movement of this area only. This is your spring work done. So work done is your 320. This is a 200 kPa. So this is a 0.05, 0.1. So the total area will be 1 over 2, 320 minus 200 times your volume is 0.05 meter cube. So this is a kPa. You got Newton meter work spring. Okay, so thank you.